Hey everybody. Hopefully this strange semester is going well for all of you. Um, so this week what I'm going to do is something a little bit different. I'm going to produce the video for your SPSS assignment 3. But before we get into that, I'm going to go over conceptually what is the chi-square, because that's what your SPSS assignment 3 is going to be predicated on. I'm going to show you how to do one really simple thing by hand. Chi-square is going to be similar to what we did for t-test, where we're going to do the simple thing by hand, and the less simple thing, the more complex thing, is something that I'll show you how it's done, but I'm not going to expect you to know how to do it by hand. That's especially going to be the case with this online semester where I can't actually, sit down and talk with any of you. So you're going to learn about the two forms of chi-square. Those two forms are the goodness of fit test and the test of independence. Now, what they both have in common with one another is they both use categorical variables. There's no continuous variables involved in the chi-square test, unlike the t-test, and then like Pearson correlation, which we're going to learn about here in a bit, or in coming weeks. The only thing you're going to be looking at is frequencies within categorical variables. Now, the goodness of fit test is the one that we're going to learn how to do by hand. And it focuses on only one variable. It focuses on a variable that comes from a sample, and you're comparing that sample to a known population. In other words, you already know what proportion of cases fall into the categories you have in a population, and so you're looking at your sample and you're simply trying to see if the proportions divvied up among the categories is different in the sample that you drew from the overall population. This is one thing that, like most things in statistics, actually makes sense, not when I'm describing in the abstract, but when I actually show you what it is and what it does. Now, the test of independence is the thing that we're not going to do by hand, but in all honesty, it's probably the one that is more useful in actual statistics, because once again, in actual statistics, it's not all that common that you have a known population that you can describe. And so a chi-square test of independence looks at two categorical variables to see if there's a relationship between those things, whether they are related or not. So for instance, you could have two categorical variables, one for if somebody has ever been divorced or not. Let's just say it's nominal. We'll say it's binary nominal variable. And it's 1 if they've been divorced, 0 if they haven't. And then the other categorical variable that you're using in the test of independence is bankruptcy. Let's say that's also a binary variable. Has somebody declared bankruptcy within their lifetime? 1 if yes, 0 if no. And so what you can do is you can use a chi-square test of independence to see if people who have been divorced declare bankruptcy less or more frequently than people who haven't been divorced. So ultimately what you're trying to do with the test of independence is you're trying to see if there's a relationship between those two things or if they're independent. And it's, the relationship, whether it's divorce and bankruptcy or any other pair of nominal variables, you're trying to see if there is a relationship between those two things. And so you can use an independent variable and a dependent variable in the chi-square test. Now, there is one problem with there's a couple problems that I should note, and I'm actually going to give you kind of a laundry list of limitations of the chi-square tests in general, but specifically for the test of independence, it doesn't show directionality. And so that can be kind of hard for hypothesis testing, because in order to prove a relationship between an independent variable and a dependent variable, you kind of have to show which one is the dependent, which one is the independent. And so since it doesn't show directionality, a pretty substantial limitation is the fact that, like, let's say you show that divorced people do declare bankruptcy at a much higher rate. Is it the bankruptcy that's causing more people to get divorced, or people who are getting divorced declaring bankruptcy? Like, you don't know that from a chi-square test. So that's a pretty substantial limitation. The other big limitation is you can do a test of independence with ordinal variables, but it doesn't really take advantage of the fact that they are ordinals. The chi-square test doesn't take into account that these are ranked. And so it just looks at how many people fall into the various categories and, tries to show if there is a relationship between the two categorical variables. So yeah, that's another limitation as well. So another big limitation is that the chi-square test doesn't show how strong a relationship is between two variables. It just shows that there is a relationship whatsoever. Like I said, doesn't show directionality. The statistic is something that is really, really sensitive to sample size. And so depending on the size of your sample, you're going to get a different result, which, I mean, that's not necessarily a limitation. That's really the case with all statistical tests. It's just something to keep into consideration. And so if you have a really, really small sample size, it's probably going to be the case that the chi-square test is not terribly useful to you. But that's kind of the case with all statistical tests. I mean, in order for a statistical test to be valid, you have to have a decent sample size. And so small sample sizes are inherently problematic all the time. And that's no different with the chi-square test, either of them. The chi-square test of goodness of fit or the chi-square test of independence. And lastly, chi-square statistically starts to become unstable when you add more and more and more and more categories to your variables. And so it's less effective when you've got a lot of different categories within a nominal variable. So for instance, if you were to do a chi-square test, either of goodness of fit or of independence, and one of your nominal variables is race, the chi-square test is going to be more effective if you have relatively few categories in that. So it's just like, if you have just black, white, Hispanic, and other 4 categories, the chi-square test is probably going to be pretty good with that. It can handle that. If you break it up into a whole lot of different categories, it starts becoming more and more problematic. And so, like, let's say you have a race variable that's like that's white, but then it breaks up into not just black but African American, and like foreign-born African, and it breaks up into all the different ethnicities of Hispanic, and so you have Venezuelan American and Mexican American and Puerto Rican American, and Mexican American, and then you break into all the different ethnicities of Asian American, and so that would be way too many categories for a chi-square test to handle effectively. And so that is one particular limitation to keep in mind with the chi-square test. The fewer categories you have, generally the more valid your test result is going to end up being in chi-square. Now, the chi-square statistic, whether it be for a test of independence or a goodness of fit test, uses the same formula. Now, you'll notice here that you've got the terrifying sum sigma symbol right here. So yeah, that sucks. You are going to have to do this. You are going to have to do this formula multiple times and then add it. Now that said, like I know that like it can be cumbersome to deal with that. We're going to do examples, and on the test, there's only going to be problems that are going to have a limited number of categories, which means you're only going to have to do this equation a handful of times and sum a handful of numbers. I'm not going to give you like something that has like 12 different categories, because then it's going to become it's going to become really cumbersome, and B, as I stated before, your chi-square test becomes less valid the more categories you end up adding to it. Yeah, do note that this is the formula. The formula is the same for both the test of independence and the goodness of fit test. What is different is how you do observed frequencies here. Now, I should break down this formula for you. So this is observed frequencies, the number of cases you expect to fall into. Are the number of cases you see fall into given categories in your sample. Expected frequencies, the number of cases you expected to fall into a given category of your nominal variable. That expectation in the case of the goodness of fit test is based on your known population, and then this is the expected frequencies as well. And then you know that this is just squared, this is the sum sigma, and this is the symbol for chi-square. Now, one thing that you have as a resource is this table. Once again, the really important thing is organizing your math, not losing track of what it is that you're doing. The math itself is not that difficult at all. It's just once you start, especially summing numbers, it can become easy to lose track of what you're doing. Now, I changed this up a little bit. So I made this table and I put it as a .doc in course resources. I did change it so it looks a little bit different. It's got the O and E I used here. Rather than writing out observed F and expected F. But yeah, just know observed F is the equivalent of O, and expected F is the equivalent of E. But I think I went ahead and made that change in the .doc. So we are going to do a goodness of fit test. I'm going to give you a few examples. Like I said, the goodness of fit test is comparing a sample that you get to a known population. So you could, for instance, try and test, is the percentage of unemployed people in Norfolk representative of the population of unemployed people in Hampton Roads in general? And so let's say you know the overall unemployment rate in Hampton Roads and you want to compare it to a sample of people specifically from Norfolk. You could do something like that. Or you could compare the proportion of youth who were obese in Sacramento, California in 2015 to the proportion that were obese in 1995. And you want to see if there's a statistically significant difference. Or you want to see if the proportion of African American men in federal prisons has changed from prior to the drug war to after the drug war. I mean, in that case, you'd probably be comparing two different populations and not just a sample to a population. You, in that case, may have two known populations. Now, the important thing is you're just comparing a sample to a population, or in some cases, a population to a population, to see if there's a statistically significant difference. Now, as is always the case when you're comparing samples or population, you know there's always going to be something of a difference because there's just randomness in the world. But you want to see if there is a difference that is so significant that it likely would not have occurred by chance. And so I am going to stop this video and then I'm going to pick back up and I'm going to show you how to do a goodness of fit test by hand using the table that I posted. Now, we are going to look at a sample, we'll say hypothetically, from Newport News in terms of political party affiliation. We're going to compare that to a known population that is all political parties in the South. And so, anyways, I'm going to stop for a second, and then I'm going to pick right back up, and we're going to actually start doing the math by hand. Okay, hey everybody. So we're going to go ahead and try out a example for the goodness of fit test. Now I'm going to give you two different examples. One that is obviously statistically significant and one that is obviously not. So these are theoretical examples. These are all made up numbers, but this example should kind of give you an idea of how this works, and will definitely give you an idea of how to go about doing it. So naturally, before you go into any statistical test, you first want to start off with your hypothesis. Now, keep in mind the limitations of the chi-square test. You can't really tell directionality with the chi-square test or strength of a relationship. So in order to make a hypothesis for a chi-square test, your null hypothesis is simply that the sample proportions and the population proportions are approximately equal. And the alternative is that they're not. There is a difference, and there is a statistically significant difference between the sample proportions and the population proportions. Now, in order to do a goodness of fit test, you're going to have to do some pretty simple calculations, but they're important. So you'll have to figure out the expected population proportions, are the expected sample proportions based on the population that you have. And you also have to calculate degrees of freedom. Calculating degrees of freedom, the same as with the t-test, is super easy. Your degrees of freedom is k minus 1, which k is just the number of categories you have in your sample and population, and you subtract 1 from that. And so our first example has 3 categories. It's based on political party affiliation: Republican, Democrat, Independent. And so our degrees of freedom that we'll eventually use in our chi-square table is going to be 2. 3 categories minus 1 equals degrees of freedom of 2. So our example, I'm going to pull from what I have in the slides. Now, the slide actually has a fully fleshed out example of working through the equation. I'm going to do a different example on the table here to show you how to do it, but I'm going to use the same proportions. So we have here what we'll say is the proportions for political party affiliation in the American South. And so we'll say we have a population in the American South, and we know that 60% or 0.60 are Republican, 30% or 0.30 are Democrat, and 10% are or 0.10 are independent. And we'll say that's a population we know. We know that is the breakdown of political party affiliation in the American South. Now, that's our population. We're going to compare it to a sample of, we'll say, 1,500 Newport News residents. And our alternative hypothesis is that Newport News, our sample of Newport News residents, will be statistically different in terms of their political party affiliation when compared to the population of all people in the American South. So this is the table that I have for you. I have a blank version of this that I posted in course resources. And this will give you an opportunity to organize your work in a way that should simplify things and keep you on track and keep this from getting overly cumbersome. So the first thing you do is you write down what your categories are. Obviously, we have Republican, Democrat, Independent. We've got 3 categories. And then you write your observed frequency within your sample. So we'll say, just hypothetically, that our sample of Newport News residents had 505 Republicans, 905 Democrats, and 90 independents. So that's what we actually observed. That's what was in the sample. The next thing you need to do is you need to calculate your expected frequencies. Your expected frequency is the proportions or the frequencies that you would see in your sample if the proportions were identical to the population. So in other words, if the Newport News political party breakdown was exactly the same as the rest of the American South, this is what you would see. And so, for instance, if it was exactly the same as the rest of the American South, 60% of our sample would be Republican. And that would translate to a frequency of 900 Republicans in our sample of 1,500. And similarly, 30% would be expected to be Democrat. That would translate to 450 Democrats in our sample of Newport News residents. Lastly, we would expect 10% to be independent, so take 0.10, multiply that by 1500, our sample, and that would give you an expected frequency of 150. So it's super simple to get the expected frequency. Just multiply the proportion that you saw in your population by your overall sample size, and that gives you what you would expect if your sample looked exactly like your population. Now you can already tell there's a difference, and this is probably leading towards statistical significance, because I mean, 505 is a way smaller number than 900, but we're going to go through the whole test to be statistically rigorous. So once you have your observed frequencies and your expected frequencies, next thing you do is you get your residual. And to get your residual, all you have to do is subtract your expected frequencies from your observed frequencies, and that's really easy. So 505 minus 900, that equals negative 395. And so that's just simple subtraction. Our next residual is 455, and our next residual is negative 60. So let's center them just so they look nice. And so once you have your residuals, the next thing that you do is you square them. And this is where you're going to start getting big numbers. Your numbers will always be positive because whenever you square something, it always ends up positive. So all you're going to do is take your residual and hit that square button on your calculator. So our first residual squared is going to be 156025. Our next residual squared is going to be 207025. And our next residual squared for independence is going to be 3600, or 3600. Now, next is the part where you actually start doing the equation. And if you remember, the equation has that sum sigma symbol. So you're going to end up doing the equation 3 times and summing all of the outcomes you get from those 3 different equations that you do. Now, what I went ahead and did here is I went ahead and did the equation for the first category, Republicans. And so you can see 505 minus 900, so expected minus observed minus expected, square that, and so that gives you our squared residual of 156025. Then you just divide that by your expected value for that category, and so that ends up giving us a end result of 173.36. Do the same thing for the Democratic category. That gives you an end result of 460.05. Do it once more for the Independents. That gives you a result of 24. Now, all you have to do is sum these. So you sum them, and that gives you 657.41. So here's our chi-square, 657.41. So that's a pretty big number, and so a pretty big number is probably indicative of a significant chi-square. So now this is where we break out the table. You also have this in course resources. Now we are going to test our hypothesis at the 0.05 level. And so we know that we have 2 degrees of freedom because we have 3 categories, k minus 1, 2. And so that gives us a critical chi-square value of 5.991. In order for you to declare you have a statistically significant difference and reject your null hypothesis, you just need your chi-square value to be bigger than the critical value you find. And so our chi-square value is way bigger. It's 657.41 compared to 5.991. So yeah, that's super significant. In fact, we could also reject our null hypothesis and by a large margin at the 0.005 level. We could probably reject it at the 0.0001 level because, I mean, that's a big difference. I mean, you see that in Newport News, you've got 550 Republicans when we would expect to have 900. So that tells you that Newport News voters are statistically significant, are different at a statistically significant level. So I am going to pause the video one more time, and then we're going to launch into another example that this time should not be statistically significant. Hey, so we're going to do one more example. This one's going to be even simpler than the previous example. And like I said, I wanted to give you an example of something that would not be statistically significant. So we're going to say that we have a sample of 2,500 CNU students, and we want to compare that to a known population in which our categories are if students live on campus or off campus. We'll say that it is the case that we know that off-campus students at American universities consist of 20% of American college students. So I'm doing this a little bit differently. I'm calculating my observed frequencies first. So we'd expect 500 in our sample to live off campus. On-campus students at American universities are 80%. Now these are made up numbers and they're probably incorrect. I actually guarantee you they're incorrect, but just for the sake of example, let's pretend. So if 80% live on campus, and we're going to expect out of our sample of 2,500 that 2,000 are going to be on campus. So we'll say our observed frequency was for off campus in our CNU sample of 2,500 CNU students was 488 living off campus, and on campus it was 2,012. So you are going to calculate your residuals. So 488 minus 500 equals negative 12. Your residual is just going to be the inverse when you only have two categories. That's something to note. But just do the math the same. So 2012 minus 2000 is naturally 12. So just the inverse. So you do your residual squared. Now your residual squared in this case is actually going to be the exact same thing because you have negative 12 and you have 12. And so you square negative 12 and 12, you get the same result of 144. So our residual squares are 144. Now, this is where you start doing your calculations. So let's say for off-campus residents, it is the case that our residual squared ended up being 144, and our expected value was 500. So you calculate 144 divided by 500. That gives you an end result of 0.288. And so you can already see we've got way smaller outcomes for our equations than we did prior. So that's your first indicator is probably not going to be significant. So you do the equation again. So once again, the residual is the residual squared is the same for on-campus livers, but we have a different expected value. So our residual is 144. We're going to divide that by our expected value of on-campus residents of 2,000. That gives us an even smaller number, 0.072. So next thing you do is you just add those. 0.072 plus 0.288, that gives you a summed end result of 0.36. So there's our chi-square number. So let's see if it is statistically significant or not. So go back to our chi-square table. Once again, we're going to do 0.05. We have even fewer degrees of freedom here because unlike the last example where we had 3 categories, now we only have 2. So we only have 1 degree of freedom. So we're going to do 0.05 alpha. And in our critical chi-square value is 3.841. Now the chi-square value that we got is 0.36. Way smaller than 3.841. And so it looks like we would not be rejecting the null hypothesis in this instance. So we would say that CNU students, in terms of where they live, are not significantly different than the general population of college students. Yeah, there is a little bit of a difference, but it's pretty safe to assume that that's just due to randomness. There isn't an actual difference between CNU and the rest of the population of college students. So that is 2 examples of how to do goodness of fit test chi-square. I'm going to go ahead and polish off the lecture, kind of give you a relative idea of what the test of independence is. And then I'll let you go ahead and launch into doing the SPS. Okay, so I'm going to keep this last bit simple and just kind of reiterate what the test of independence is. Like I said, you'll be doing this in SPSS. You're not going to be doing this by hand. I do have the math here in the slides to kind of give you an idea of how it's done by hand, but this does have the potential to be way more cumbersome than the goodness of fit test. And so especially in this kind of unique semester in which I can't, be there physically to aid you in this, we're not going to do this, but or at least by hand. Now, the test of independence, like I said, is you're looking at 2 different nominal variables or ordinal variables, which is 2 different categorical variables of any type, to see if they are related to one another. The test of independence is basically testing the null that the 2 different variables are independent, meaning they don't really impact one another whatsoever. And so you could test, for instance, is there a relationship between a religious affiliation and opinions on abortion? In this case, you would probably be using like a Likert scale variable, where it's like how do you feel about abortion? And it could range from 4 categories: extremely disagree with abortion, somewhat disagree with abortion, somewhat agree with abortion, or agree with we'll say the notion abortion should be legal. So extremely disagree with that notion, somewhat disagree with that notion, somewhat agree with that notion, or extremely agree with that notion. And so there's your 4 categories, and then you could test that against religious affiliation. Let's say you break that up into non-religious and Christian and Jewish and Muslim and other. So you could see if the proportions of agreement or disagreement are different among the different religious categories. Are women more likely than men to get a college degree? So this would be really, really simple. You could just compare 2 binary variables, male and female, and has a college degree, does not have a college degree. Is within those categories, is there a difference? Do you see a higher proportion of people with a college degree who are female than male, or vice versa? Or is there not much of a difference at all, at least not a statistically significant one? are young adults less likely than middle-aged adults to be married. So you could do, once again, a binary variable, young adult for one category and middle-aged adult for another category, whatever cutoff age you determine is appropriate. And you see, you look, at the results based on another binary variable. Are you married or are you not married? So this is something that I think is going to be a little bit, I mean, it's pretty straightforward, but I think it's something that's going to be a little bit more clear once you see it in action in SPSS. Now, for hypothesis testing for this, your null hypothesis is that the two variables are independent. So if they're independent, it means they don't have anything to do with one another. So let's say it's the case that gender and getting a college degree are independent. Then you would probably expect about the same proportion of men in a sample to have a college degree as, the proportion of women in a sample. So the alternative hypothesis, oftentimes expressed H1, is two variables are not independent, which means they are dependent. So you would end up seeing a difference. So if there was, a dependent relationship between gender and getting a college degree, you would see a difference. Either more men in your sample have a college degree than women, or more women in your sample have a college degree than men. Now, in order to do this, you end up having to get your expected values by looking at the margins of your columns. Now, this is where it gets more complicated compared to goodness of fit. You end up getting equations that look like this. And like I said, it can be cumbersome. I think it's something that, especially with really simple examples, I think it's something that you could do, but we're not going to go ahead and attempt to do it in the current circumstance we're in, where we're 100% online. Now, one thing to note is that when you do a test of chi-square, whether it be goodness of fit or a test of independence, it is always an upper tail test, which what it functionally means is always reject the null hypothesis if the calculated chi-square value is greater than or equal to the critical value. So it's super simple to do a chi-square test and use the chi-square table. Is the number you came up with bigger or the same as the critical value? If yes, then you get to reject the null. If it's not, if it's smaller, then don't reject the null. You still maintain your null hypothesis. So you already have this. Here's your chi-square table. You use it similarly to your t-test table. So just figure out the degrees of freedom. Remember k net -1, and then find that's your row, and then find your column with your alpha. So for 4 degrees of freedom, or you have 5 categories, and you want to use an alpha of 0.05, as we've generally been using in this class, then your critical chi-square value is going to be 11.07. And so if you come up with a chi-square that is the same or equal to 11.07, then you get to reject your null. So there's the formula. Like I said, you'll use that. I mean, that's the formula for both goodness of fit and test of independence. The difference between the two is finding the expected value. It's more complicated to find the expected value in the test of independence, but the formula is exactly the same. So always remember to sum all your results to get your chi-square. And yeah, that's basically it. That's all I want you to learn conceptually and in terms of doing math by hand when it comes to chi-square. Next, we'll move on to actually doing chi-square tests in SPSS. Hey everybody, so I am going to go over assignment 3 with you. I have not posted this yet, but it will be posted by the time I post the video, but this is the assignment. Right now, I do need to update some things. You'll see I have the points here. Those need to be updated. One of the changes I'm making from the previous semester to this semester, is taking out part of this assignment. Part of this assignment was actually intended to be analysis of variance. There was originally 2 tests that were part of this assignment that the fall semester did, but since we're online only, I'm going to go ahead and nix analysis of variance from the agenda altogether. So that was the 3rd part of this assignment. There was originally a part C. Now there's just part A and B. Both involve chi-square testing. And so since I got rid of part of the assignment, I need to adjust the point values. But note that there are 2 parts of this assignment. So the very first thing you should do before starting this assignment is do case selection. Like the previous assignment, this assignment has an element of case selection. This is simpler, and actually you'll keep the same cases selected throughout the entirety of it, but you are just going to select cases that are from the year 2010 and onwards. So your syntax is just going to be the year variable and then greater than or equal to 2010. And you'll leave that on throughout the entirety of the assignment. For those of you who inevitably slipped up in the second assignment by not taking off your case selection when you were done with it and moving on to a different assignment, you shouldn't have that problem in this assignment, though you should always be mindful of when you have case selection on. But this assignment uses the same cases throughout Part A and Part B. So this assignment is going to involve a chi-square test of independence. So you are going to try and see if there's an association between 2 nominal variables. And then you are going to add in a layer. A layer makes more chi-square tests based on an additional nominal variable. So that makes a little bit more sense once you see it in action. You are going to be doing initially a chi-square test that examines the association between attitudes towards marijuana legalization, the grass variable, and respondent sex. And so the grass variable is a Likert scale variable that asks people how much do they agree with marijuana legalization. I believe there's 4 categories that range from like strongly disagree to strongly agree. There may even, off the top of my head, I think there may even be like a neutral in there, but it's just a handful of categories that are ordinal that look at how much people agree or disagree with the notion of marijuana legalization. And then the sex variable is a standard binary variable for male and female. Now, what you will be doing in Part B is you're going to be adding religion on top of that, specifically a binary variable for whether somebody is Christian or not Christian. And so you'll actually end up doing, for this Part B, you'll end up having 3 different chi-squares that are produced. One for among people who are Christian, one for among people who are not Christian, and one for the sum total combined of both Christians and non-Christians. Like I said, I feel like that becomes a little bit more clear once you go ahead and get into it and start doing it. So the first thing you will do in order to set up your chi-squares, you're actually going to go to Analyze, and you're going to go to Descriptive Statistics. It's a little counterintuitive, but SPSS has chi-square as actually an add-on to crosstabs, which crosstabs are a form of descriptives that are used for nominal variables. So you go to crosstabs. So I am going to do a different example from what your actual assignment is. I am going to look at the relationship between divorce and overall happiness. Now, our dependent variable in this is happiness, and it is, I believe, a 3-category ordinal variable that asks people how happy they are. And then divorce is a simple binary variable that just states if somebody has been divorced or not in their life. And so we're going to look and see if there's a difference in terms of overall reported happiness among those who have and who have not been divorced. So you'll set up your crosstabs the way I have here, you're going to put your dependent variable in the columns, which is generally how it's done. It can go either way. You can put it in the rows, but most of the time, for most variables, it makes more sense to put your dependent variable in the column and your independent variable in the row. So happiness is our dependent variable and divorce is our independent variable. Now the next thing you are going to want to do, and this is really, really, really important, click on statistics, make sure chi-square is clicked. Like I said, this is an add-on to the crosstab function. So make sure that you have chi-square clicked. Next thing you're going to do is you're going to go to cells. Now, your crosstab should give you some percentages. Now, it's not absolutely necessary in order to do the chi-square, but it makes your crosstabs much more interpretable. So you absolutely need to be doing this. So click on percentages for wherever your independent variable is. In this case, and in most cases, it's going to be in your row. So for divorce. So make sure that that is clicked. So once you have that done and you're all set up, in all honesty, you're just ready to roll. So you will get this, or something that looks like this. This is your crosstab right here. Here you have your cases and like missing percentage, but the first real important information is your crosstabs. And so this is the proportions of people who report being very happy, pretty happy, or not too happy among those who have been divorced or in those who have not been divorced. And so you can see that among those who have been divorced, 36% about are very happy. For those who have been divorced, 36% are very happy, 53% are pretty happy, and then just under 11% are not too happy. For those who have never been divorced, 38.4% are very happy, 52.5% is pretty happy, and just over 9% is not too happy. And then you can see the totals among the combined categories. Now, you can kind of see what the trends are just by looking at your crosstab. But if you want to know if the difference is statistically significant, then you need to look at your chi-square. Now, you get several numbers here. You get actually 3 different p-values. I can tell you that for for what we are doing, the important p-value is Pearson chi-square. This is the one you need to be interpreting. You can see it's significant here. It's in fact significant at the highest level. It's significant at a 0.05 level. It's significant at a 0.01 level. It's even significant at a 0.001 level. So this is very significant. This is the chi-square value, the value that you actually calculated by hand when you were doing the goodness of fit test. But so, you could actually take this value and you could take it to a chi-square table and you could, verify, by yourself if you wanted to that it was indeed significant. But this shows you with our p-value that it's indeed quite significant. And, you can see that there is some differences in the crosstabs. For instance, almost 2% more of those who have been divorced say that they're not too happy when compared to those who have been divorced or separated. Now, who have never been divorced or separated. So now that seems like a relatively small difference, and it is, but it's statistically significant because we have a really big N. We have a lot of cases. You can see here that this was a question that was asked a lot in the SPSS surveys. And so we end up getting a number of cases of over 37,000. And so generally speaking, with most statistical tests, in fact all statistical tests, in this case chi-square, the bigger your n is, the smaller the difference has to be in order for it to be significant. I can tell you that if we saw like a 2% difference here and these marginal differences here, but we only had like an n of maybe like 100, it probably wouldn't be significant. But since we have an n of over 37,000, then that is significant. So that's the gist of what you're going to have to do for the first part of the assignment. This is pretty simple, and I'm not gonna lie, I think this assignment is probably going to be even more simple than the t-test assignment, and it certainly should take you less time to do. I do want to show you a couple more things though before we go. I want to show you how to do part B, which is to add a layer. So you're just going to go back to where you were, go to crosstabs, and you add a layer for whatever additional variable you want to account for. So it's going to be the case in your assignment you're going to create a binary variable for Christian or non-Christian. In this, we'll do another binary variable. For the example, we'll do sex. This is already created for us. So you add your additional variable as the layer, and this is what you get. You actually end up getting 3 crosstabs in 3 chi-squares. So you can see that it is the case that you have here the same thing we did previously, examining the relationship between being divorced or ever being divorced and happiness, but you have it broken up into males, females, and total. The total is exactly what we had previously. So you can see that for males, it looks like immediately off the bat, it looks like the difference between males and females in terms of the impact of divorce on happiness, or at least the relationship between divorce and happiness, seems to be different. There's about a 1% difference in the not too happy category between divorced and never divorced for males. But for women, that's substantially higher. It's up towards 3%. And so, like, you see bigger differences over here as well. And so that is something that is interesting. Actually, this is really particularly interesting because you can see that there is a statistically significant relationship between being divorced and happiness for women, and not a statistically significant relationship for being divorced in men. And so we have just stumbled upon a actual interesting, statistically significant trend that is actually something that it seems to be indicative of something in society. So, like, just by going through this example, we've actually discovered something that I did not anticipate discovering. Exactly why it is the case that for women, divorce impacts happiness more than men is up for debate, but that seems to be what we have found. And with this pretty stark contrast, with a really high overall number of cases. We've got 16,000 men in our sample, and we've got 21,000 women in our sample for a total of over 37,000. So that is layering. Like I said, you in essence get 3 different chi-squares. You've got the chi-square for male, chi-square for female, and then the total chi-square. And then you've got the same thing with the crosstabs. The crosstabs for male, crosstabs for female, and then the total crosstabs. So you will be doing something similar to that. You'll be adding religion. Now, I'm actually lastly going to show you something that I've already shown you before. I'm going to show you creating a new variable for religion, just because I've gotten several emails, and I think that some of you have been kind of stumbling on creating a new variable. So what you're going to do is you're going to create a binary variable that's going to serve as your layer. that's going to be if a person is Christian or not Christian. And so they don't have that already in the SPSS, so you have to make it. And so you're going to recode into different variables, and you're going to base this based on the relig variable. So relig variable is just a variable that's the respondent's religion. So the output variable, our binary variable, is going to be, we'll call it Christian, label R is Christian. So it is the case that we know that in the religion variable, Protestant is coded 1, Catholic is coded 2, Orthodox Christian is coded 10, and Christian is coded 11. All responses that somebody could, just put in the same category of being Christian. Maybe different forms of Christian, but in our binary variable, they all go into the category of being Christian. So the old value 1 equals the new value of 1. So we'll keep that as is, actually. The old value 2 for Catholic equals 1 for our binary variable for is Christian. Old value of Orthodox Christian being 10 is also a 1 because they count as Christian in our binary variable. And then the catch-all Christian is 11. So that's also going to be coded 1. So then the easiest thing to do is just all other values in the religion variable, 0. Those are those who are counted as non-Christian. So hit change. You've got your old and new variables. Done. So the next thing you naturally want to do is change your value labels. So value labels 1 is Christian. 0 is not Christian. So that is done. Go ahead and test it. Look at frequencies just to make sure it all makes sense. There you go. It looks like that about 83% of our sample is Christian, which makes sense. Like this, right at a glance, I can say makes a lot of sense because I know that this sample from the GSS is solely Americans, and so it also goes from 1972 all the way till basically today. I think until like 2018. Or at least 2016. And so, yeah, that sounds about right. About 83% identifying as some sort of Christian among Americans throughout that time frame. That seems to make sense. And so it looks like we went ahead and created a variable that is perfectly valid. So anyways, that is the extent of what you're going to be doing for assignment 3. Like I said, it should be less labor intensive, less time consuming than assignment 2. I've got a little narrative built in here, so maybe it's somewhat more interesting and kind of help you come up with, identify null and alternative hypotheses. Like I said, I'm going to edit this a little bit just in case you're reading this on the video. It's probably going to be a little bit different when you actually open it up on in as a Word doc from course resources. But yeah, that's basically the extent of what you'll be doing. Hit me up if you have any questions. Everybody stay safe, stay productive, try and avoid boredom. Yeah. Once again, I do miss y'all. I miss class. I miss being on campus. And I'm very much looking forward to the fall. But yeah, in the meantime, stay hunkered down, do what you need to do to make sure that you're keeping those around you safe and yourself safe. And yeah, if I don't talk with you online, I'll talk with you very soon. All right.